It's given that the system function of a LTI system is given as h of z is equal to 1 by 1 minus 1 by 4 z inverse multiplied by 1 minus 2 z inverse. If the system is stable, we need to find the value of h of 0. From the possible ROCs of h of z, we see that 1 by 4 less than mod z less than 2 is the correct ROC because in this case the system would be stable. So for finding the value of h of 0, first we split h of z into partial fractions as shown, that is h of z is equal to a by 1 minus 4 z inverse plus b by 1 minus 2 z inverse. This upon simplification becomes a into 1 minus 2 z inverse plus b into 1 minus 1 by 4 z inverse, which is as a whole divided by 1 minus 1 by 4 z inverse multiplied by 1 minus 2 z inverse. So upon equating the numerator terms, we see that the constant term is a plus b is equal to 1 and the coefficient of z inverse is minus 2a minus b by 4 is equal to 0. That implies 8a plus b is equal to 0. So b would be equal to minus a minus 8a. From this we see that a is equal to minus 1 by 7 and b is equal to minus 9 by b would be equal to 8 by 7. So from this we see that the system function h of z is equal to minus 1 by 7 multiplied by 1 minus 1 by 4 z inverse plus 8 by 7 multiplied by 1 minus 2 z inverse. So from the given ROC of the system 1 by 4 less than mod z less than 2, we see that the ROC of the first term would be mod z greater than 1 by 4 and the ROC of the second term would be mod z less than 2. From this we see that the impulse response of the system can be written as minus 1 by 7 multiplied by 1 by 4 whole power n u of n and minus 8 by 7 multiplied by 2 power n multiplied by u of minus n minus 1. From this we see that h of 0 is equal to minus 1 by 7. So for the given stable h of z, we see that the value of h of 0 is equal to minus 1 by 7. Now let us consider another problem as per which the pole 0 plot of a LTI system is given as shown. So there are poles at 1 by 2 and 2 and there is a 0 at minus 1 by 3. If the system is causal and stable, find the ROC of h of z. From the given poles, we see that ROC should be bounded by poles and it shouldn't contain any poles. So the possible ROCs are mod z less than half, half less than, mod z less than 2, and mod z greater than 2. For the first ROC, that is mod z less than half, the system would be anti-causal, hence non-causal, and unstable as it doesn't include unit circle. For the second ROC case, the system would be non-causal and stable. And for the case of third ROC, we see that the system would be causal and unstable. From this, we see that there is no ROC of h of z which leads to causality and stability. From this, we see that ROC satisfying the given conditions doesn't exist. Now, let us consider another problem as per which the system function of a LTI system is given as h of z is equal to y of z, sorry, 2 by 1 minus 2z inverse multiplied by 1 minus 3z inverse. We need to find the LCCDE that represents the LTI system. The system function of the LTI system can be written as h of z is equal to y of z divided by x of z is equal to 2 by 1 minus 2z inverse multiplied by 1 minus 3z inverse. So upon simplifying this equation, we get that y of z multiplied by 1 minus 5z inverse plus 6z power minus 2 is equal to 2 into x of z. By taking the inverse transform on both sides, we get that LCCDE is y of n minus 5 into y of n minus 1 plus 6 into y of n minus 2 is equal to 2 into x of n. So this is the LCCDE that represents the given LTI system. Now let us consider another problem as per which it is given that the system function of a non-causal LTI system is given as 2 by 1 minus 2z inverse 1 minus multiplied by 1 minus 3z inverse. Please note that it is given that the system is anti-causal. We need to find the LCCDE, that is linear constant coefficient difference equation that represents the LTI system. The given system function h of z can be written as h of z is equal to 2z square divided by z minus 2 multiplied by z minus 3. This is equal to 2z square divided by z square minus 5z plus 6. This is equal to y of z divided by x of z. So upon simplifying this, we get that y of z multiplied by z square minus 5z plus 6 is equal to 2z square x of z. From this we see that by taking the inverse z transform on both sides, we get that 6 into y of n is equal to 2 into x of n plus 2 minus y of n plus 2 plus 5 into x of n plus 1. So the LCCD that we obtained corresponds to a anti-causal system function given. Now let us consider another problem as per which it is given that the system function of a LTI system is h of z is equal to 2 minus 3 by 4 z inverse divided by 1 minus 3 by 4 z inverse plus 1 by 8 z power minus 2. There are three statements given as related to the system function. One is the system is stable and causal for the ROC mod z greater than half. The second one is the system is stable and non-causal for the ROC mod z less than 1 by 4. And the third statement is the system is neither stable or unstable and non-causal for the ROC 1 by 4 less than mod z less than 1 by 2. We need to find out which of these statements are correct. We see that the given system function h of z has poles located at 1 by 4 and 1 by 2. From this, we see that the ROCs are mod z greater than 1 by 2, 1 by 4 less than mod z less than 1 by 2, and mod z greater than 1 by 4. From this, we see that in case of the first ROC, the system is stable and causal. In case of second ROC, we see that the system is unstable and non-causal. In case of third ROC, sorry. The third ROC is mod z less than 1 by 4. In case of third ROC, the system is anti-causal, non-causal, and unstable. From this, we see that the statement 1 is correct, the statement 2 is not correct, and the statement 3 is correct. So, for the given system function, we see that the statements 1 and 3 are correct. Now, let us consider another problem as per which there is a discrete time signal given as x of n is equal to 1 by 3 whole power n u of n minus 1 by 2 whole power n u of minus n minus 1. We need to find the ROC of the Z transform of x of n. We know that the Z transform of x of n is given as Z transform of 1 by 3 whole power n u of n minus Z transform of 1 by 2 whole power n u of minus n minus 1. So the Z transform of 1 by 3 whole power n u of n is 1 minus 1 by 3 Z inverse, and the corresponding ROC is mod Z greater than 1 by 3 minus the Z transform of 1 by 2 whole power n u of minus n minus 1 can be written as 1 minus half Z inverse with an ROC of mod Z less than half. From this, we can say that the Z transform of x of n will have an ROC of the intersection of mod Z greater than 1 by 3 and mod Z less than 1 by 2. From this, we see that the ROC of Z transform of x of n is 1 by 3 less than mod Z less than 2. Now, let us consider a problem as per which there is a network given as shown in the figure. It contains a 5-volt source and a switch S which is closed at t is equal to 0 and a 10 microfarad capacitor and 200k resistor. The output of the resistor is given to a sampler which samples at Fs is equal to 10H, and the obtained output of the sampler is X of n. We need to find X of n from the given network. From the given network, we see that the voltage drop across the 200k resistor can be given as VR is equal to 5 into e power minus t by tau u of t, where tau is equal to r into c, that is equal to 2 millisecond. From this, we can write that VR is equal to 5 into e power minus t by 0.002, that is equal to 5 into e power minus, sorry, tau is equal to 2 second. From this, we can say that VR is equal to minus t divided by 2. So that implies VR is equal to 5 into e power minus 0.5 t u of t. It's given that the sampling frequency Fs is equal to 10H. That implies the sampling interval Ts is equal to zero point 0.1 second. So upon substituting t is equal to n into Ts, we get that x of n is equal to the sampled version of Vr of t is equal to 5 into e power minus 0.5 into n into zero point 0.1 u of n. which can further be simplified as 5 into e power minus 0.05 n u of n. So the output of the sampler is given as 5 into e power minus 0.05 n u of n. Now let us consider another problem as per which it is given that a signal x of n has a z transform of zero point 0.5 divided by 1 minus 2z inverse. It's given that the ROC of x of z includes unit circle. From this, we need to find the value of x of 0. For the given x of z, we see that the possible ROCs are mod z less than 2 and mod z greater than 2. From this, we see that the possible ROC of the system, ROC of the x of z is mod z less than 2 as it includes the unit circle. From this, we can write that x of n is equal to zero point 0.5 multiplied by minus zero point 0.5 multiplied by 2 power n u of minus n minus 1. From this, we can write that x of 0 would be equal to 0. So, for the given x of z, if the ROC includes unit circle, x of 0 is equal to 0. Let us consider another problem as per which there is a causal LTI system with the LCCDE as y of n is equal to 1 by 3 multiplied by y of n minus 1 plus x of n plus 2. It is connected in cascade with another LTI system of impulse response h of n is equal to delta of n minus 1 plus delta of n minus 3. We need to find the LCCDE that represents the cascaded system. From the given data, we see that the system function of the system 1 can be written by taking z transform on both sides as h of z is equal to y of z by x of z is equal to z square divided by 1 minus 1 by 3 z inverse. This is the system function of the first system, and for the second system h2 of z is equal to z power minus 1 plus z power minus 3. From this, we see that the system function of the overall system can be written as h1 of z plus h2 of z. This is equal to z plus z power minus 1 divided by 1 minus 1 by 3 z inverse. This is should be equal to y of z divided by x of z. As the individual systems are causal, the overall system would be causal as well. So we see that the LCCDE can be simplified as by taking the inverse Z transform 1 y of n minus 1 by 3 y of n minus 1 is equal to x of n plus 1 plus x of n minus 1. Sorry, here this is n minus 2. So this would be z power minus 2. So this would be z power minus 3 and z power minus 5. So y of n minus y 1 by 3 y of n minus 1 is equal to x of n minus 5 plus x of n minus 3. This is the LCCDE of the overall system. Now let us consider another problem as per which a causal LTI system is represented by the difference equation 2 into y of n is equal to alpha into y of n minus 1 minus 2 into x of n plus beta into x of n minus 1. It is given that the system is stable, then we need to find the condition that needs to be satisfied. Thus, by taking the jet transform on both sides, the system function can be written as h of z is equal to y of z by x of z is equal to minus 2 plus beta z inverse divided by 2 minus alpha z inverse. From this, we see that the possible ROCs are mod z greater than 2 by mod alpha and mod z less than 2 by mod alpha. But it is given that the system is causal, so the second ROC is not a correct ROC. So the first ROC, that is mod z greater than 2 by mod alpha, is the correct ROC. But it is given that the system is stable, so 2 by mod alpha should be less than 1, as the ROC should include unit circle. From this, we see that if the system is stable, the correct condition that needs to be satisfied is mod alpha greater than 2 and for any value of beta. Now let us consider another problem as per which it is given that h of z is equal to 1 by 1 minus 2z inverse multiplied by 1 minus 3z inverse. It's given that the system is causal. Then comment on the stability of the system. Here we see that as the system is causal, the possible ROC of the system is mod z greater than 3. As mod z greater than 3 is the ROC, the system would be unstable because it doesn't include unit circle. From this we see that for the given h of z, if the system is causal, it should be unstable. Now let us consider another problem as per which there are two signals x of n and y of n whose z transforms are given as x of z is equal to 1 minus 3z inverse and y of z is equal to 1 plus 2z power minus 2. It's given that the impulse response of a LTI system is given as h of n is equal to x of n minus 1 convolved with y of n, where star represent discrete time convolution. Now, for the same LTI system, if an input of delta of n minus 1 is given, find the output. So, from this, we see that h of z is equal to z transform of x of n minus 1 multiplied by z transform of y of n. We know that z transform of x of n minus 1 is equal to z inverse of x of z and z transform of y of n is equal to y of z. So upon substituting for x of z and y of z, we get that h of z is equal to z inverse of 1 minus 3z inverse multiplied by 1 plus 2z power minus 2. When an input of delta of n minus 1 is given, the output is h of n minus 1, which will have a z transform of z inverse into h of z, that is equal to z power minus 2 multiplied by 1 minus 3z inverse multiplied by 1 plus 2z power minus 2. This can further be simplified as z power minus 2 minus 3z power minus 3 plus 2 z power minus 4 minus 6 z power minus 5. From this, we see that the output, that is h of n minus 1, can be given as 0 comma 0 comma 1 comma minus 3 comma 2 comma minus 6, where the first 0 corresponds to the instant n is equal to 0. Now let us consider another problem, as per which there is a signal x of n which has a z transform of x of z is equal to sigma n is equal to 0 to infinity 3 power n divided by 2 multiplied by z power 2n. This signal is orthogonal to, we have to pick the correct option out of the options A, B, C, and D, in which the jet transforms are given as sigma n equal to 0 to infinity 2 by 3 whole power n z power minus n, sigma n equal to 0 to infinity 5 power n z power minus of 2n plus 1, sigma n equal to minus infinity to plus infinity 2 power minus mod n z power minus n, 2 z power minus 4 plus 3z square plus 1. We see that the given signal x of n is non-negative, or rather say positive, and also all the signals in given in the options A, B, C, and D are positives in value in time domain. From this, we see that the given signal x of n is present only at even instants, and the signal in the option B is only present at odd instants. So sigma x of n y star of n is equal to 0. So the signals x of n and y of n are orthogonal, where y of n corresponds to the signal in option B. So option B is the correct answer. Now let us consider another problem, as per which it is given that an LTI system is represented by the difference equation y of n minus 1 by 3 y of n minus 1 is equal to x of n, and an input of x of n is equal to 1 by 2 whole power n u of n is given to the system. If the system is initially at rest, find the output y of n of the LTI system. We see that the given LTI system has the system function of h of z is equal to y of z by x of z is equal to 1 by 1 minus 1 by 3 z inverse, and the z transform of the input is equal to 1 by 1 minus 1 by 2 z inverse. From this, we see that the output of the LTI system is y of z is equal to h of z multiplied by x of z, which can be written as minus 2 divided by 1 minus 1 by 3 z inverse plus 3 divided by 1 minus 1 by 2 z inverse. Also, we see that the system function h of z is causal, so it has an ROC of mod z greater than 1 by 3, and the input x of z has an ROC of mod z greater than half. So if we see the ROCs of individual terms, we see that the first term has an ROC of mod z greater than 1 by 3, and the second term has an ROC of mod z greater than half. By taking the inverse z transform, we get output as y of n is equal to minus 2 into 1 by 3 whole power n u of n plus 3 into 1 by 2 whole power n u of n. So this is the output of the given LTI system. Now let us consider another problem as per which the z transform of a signal x of n is given as x of z is equal to 1 by 2 divided by 1 minus a z inverse plus 1 by 3 divided by 1 minus b z inverse. It's given that mod a and mod b are less than 1 and the corresponding ROC is specified as mod a less than mod z less than mod b. We have to find the ROC of the we have to find the value of x of 0 for above sequence. From the given x of z, we see that the first term is 1 by 2 divided by 1 minus a z inverse. It corresponds to an ROC of mod z greater than mod a. And the second term is 1 by 3 divided by 1 minus bz inverse. It corresponds to an ROC of mod z less than mod b. From this, we see that the inverse z transform of x of z, that is x of n, is given as 1 by 2 multiplied by a power n into u of n plus 1 by 3 multiplied by minus b power n u of minus n minus 1. From this, we can get x of 0 as upon substituting n is equal to 0 half. So for the given x of z, we see that x of 0 is equal to half. Now let us consider another problem as per which it is given that the impulse response of a LTI system is h of n is equal to minus 5 power n multiplied by u of minus n minus 1. Then we need to find the system function of the system along with the ROC. We see that the system function h of z is equal to z transform of h of n is equal to 1 by 1 minus 5 z inverse, and the corresponding ROC is mod z less than 5. So here we see that the system is stable and anti-causal because the ROC includes unit circle and the ROC is inside a circle. Now let us consider another problem as per which it is given that two systems of system function h1 of z and h2 of z are connected in cascade. It is given that h1 of z is equal to 1 minus 0.4 z inverse divided by 1 minus zero point 0.6 z inverse, and it is also required that the cascaded system should have the impulse response as a unit delay, that is delta of n minus 1. From this, we need to find the system function h2 of z. As per the given data, the overall system function is given as h1 of z multiplied by h2 of z is equal to z inverse. From this, we see that h2 of z is equal to z inverse divided by h1 of z. This upon simplification or sorry, this upon substitution for h1 of z becomes z inverse of 1 minus zero point 0.6 z inverse divided by 1 minus zero point 0.4 z inverse. So based on the given condition and given h1 of z, we see that the system function of the second system, that is h2 of z, is equal to z inverse of 1 minus zero point 0.6 z inverse divided by 1 minus zero point 0.4 z inverse.